mainly dominated by gate delay. So if your design met timing in synthesis, you could throw it over the wall to the place route team, and the design would meet final timing without requiring a lot of timing-driven features. This was using what we call a gate-centric flow. That simplicity changed around 180 nanometers when interconnect capacitance started to be a dominant factor of total timing path delay. Here, path timing became dependent on cell placement.
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Electronics will be pervasive as companies move from selling hardware to providing personalized digital services. IoT will connect everything with automation and intelligence to optimize performance. It's all enabled by digital threads that turn silo data into connected disciplines and processes. These threads form the neural network of a digital twin, a virtual entity which mirrors the physical world, turning data into insight to continuously design, build, and optimize throughout the product and production lifecycle. This transforms siloed electronic systems development, enabling intelligent simulations and parallel design to front-load quality control. Synchronizing data throughout the supply chain and manufacturing process improves productivity and allows manufacturers to diagnose potential obstacles and avoid them. An integrated lifecycle with requirements, planning, and execution in a single system allows complex products to be developed faster and with a full collaboration of all stakeholders. Siemens can help you achieve rapid digital transformation, powered by the world's most comprehensive digital twin. There's no need to dream about the future. It's already here.
Hi, and welcome to our presentation on accelerating time to design closure and silicon success for advanced process node SoCs. My name is Wei Tan. I'm a product manager for the Solido Characterization Suite at Siemens EDA, and I'm joined today by Henry Chang, Senior Director of Product Management for the Priza Group at Siemens EDA. We'll start with a recap of the main challenges on design closure at advanced process nodes and cover the digital methodology requirements for this category of designs and how they're addressed. After that, we'll describe how a Priza digital implementation and Solido Characterization Suite address these challenges, along with results and example case studies of applying these methods in production flows, followed by a summary and wrap-up. Let's start with advanced node design challenges. Digital implementation has evolved throughout the past couple of decades, from 65 nanometer process technology to the latest cutting-edge 5 nanometer and smaller nodes. Due to silicon manufacturing limits, smaller transistor and interconnect feature sizes, and designs becoming more complex in general, several challenges have emerged for digital implementation teams. One of these challenges is pre-route to post-route correlation. As process technology shrinks, wire widths become extremely thin, especially for multi-patterning metal layers. Because of this, resistivity has become the main contributor to timing in traditional flows. This introduces a larger number of iterations needed for design closure and extra margins padded at the pre-route stage, which generally causes over-design and ultimately suboptimal power, performance, and area in the final design. Another design challenge is that the number of process, voltage, and temperature corners, or PVT corners for short, have increased drastically. Coupled with additional sign-off timing modes, this results in more than 100 multi-corner multi-mode or MCMM scenarios that have to be evaluated during sign-off. In addition, the effects of on-chip variation, or OCV, have become a major factor in timing and power, and may even exceed the impact of regular timing and power data in nominal liberty timing models. We'll go through each of these in more detail in the next few slides. Let's talk about pre- to post-route correlation first. The semiconductor industry has seen a few paradigm shifts over the years, one of them being the basic considerations for placement route. The first generation placement route was simply the placement and routing of all instances in the design. Interconnect delay was negligible, and design timing was mainly dominated by gate delay. So if your design met timing in synthesis, you could throw it over the wall to the placement route team, and the design would meet final timing without requiring a lot of timing-driven features. This was using what we call a gate-centric flow. That simplicity changed around 180 nanometers when interconnect capacitance started to be a dominant factor of total timing path delay. Here, path timing became dependent on cell placement. This created a need for more timing-driven placement solutions called placement-centric flows. The timing-driven placement had to converge before you could hand it off to routing, but in most cases, the final timing was met without specific need for accurate prediction of the detailed routing topology. The most recent shift is when moving to 16 nanometer and smaller process nodes. Because of shrinking line widths, particularly in multi-patterning layers, resistance has become more dominant than capacitance in the total path delay, and wire resistance depends on not only the length and width of the wires, but also on the detailed routing topologies such as routing layers, vias, and routing patterns, all which needs to be understood in the placement stage in order to accurately predict the timing of your design. This forms the basis of the detailed routing centric approach that we will describe in more detail in the latter section of this presentation. To visualize how traditional placement-centric approaches suffer severe correlation problems between the pre-route timing estimation and actual post-route timing, use the correlation plot shown. Here, perfect correlation would be a single line at a 45-degree angle, while differences in pre- and post-route timing are noted as points that diverge from that 45-degree middle line. At 65 nanometer, the pre-route Steiner delays versus final routed delays are mostly correlated. At 28 nanometers, the correlation starts to diverge a bit, but is still generally acceptable. And at 16 nanometers, it gets quite bad and can severely impact timing closure and power performance in the area of the final design. Finally, at 7 nanometers, we have an almost random plot where the predicted delay in the pre-route stage almost has no bearing on the post-route delays. To summarize this point, at advanced process nodes, placement engines cannot produce conversion results without information of detailed routing topology today, which is a shift in the basic factors being considered by traditional placement route tools that assume detailed routing only comes after placement and placement-based optimization. The second challenge we mentioned was the explosion in number of multi-corner multimode scenarios, or MCMM scenarios for short. The number of scenarios in MCMM timing and optimization are based on number of process, voltage, and temperature, or PVT corners, as well as the number of design modes that all need to pass static timing analysis. The biggest culprit behind this rapid increase is the large number of PVT corners needed for sign-off STA. Today, at 7 nanometers, having 50 to 100 PVT corners used at sign-off is quite common. This is compared to only a handful of PVT corners required at 65 or even 40 nanometer designs. There's no longer a best case or worst case corner, so many corners in between have to all be timing validated. Due to the same reason, optimization at the implementation stage and especially ECO changes have to be internally timed for a large number of MCMM scenarios so that the end result can match with final sign-off STA. In addition, as the number of PVTs grow, we run into an increasingly common issue where the Liberty models for the specific PVTs needed for sign-off STA or MCMM optimization is not readily available. In this case, the design team is left with two rather unappealing choices of either trying to characterize a new PVT from scratch with limited characterization information of the rest of the corners, or applying derates or interpolation to mimic the timing behavior of the uncharacterized PVT corners. Here, we'll illustrate why characterizing missing PVTs is such a challenge. Aside from requiring SpiceNet lists and Foundry PDKs that sometimes are not readily available to digital teams, there is also a significant amount of setup to run a characterization job, which is where factors such as library timing margin and other modification factors are commonly introduced. Without knowledge of this information, digital implementation teams often end up with characterizing a certain PVT, only to find that it has a systemic offset compared to the original set of PVTs like shown here. Even worse, these systemic issues are difficult to detect because unless we're looking across PVTs, like shown here, everything may seem correct by looking only at one PVT. On the other hand, as mentioned earlier, using straight interpolation or derates will lead to inaccurate results because these methods typically don't factor in nonlinear behavior within paper data or across PVTs. Without a reliable way to obtain .libs at the required PVTs, any kind of multimode multi-corner STA will run into problems, and design teams end up with incorrect timing, power, or noise calculated by STA. This leads to overdesign and schedule delays, or in severe cases, silicon failure. The third design challenge we will discuss today is on-chip variation. To provide some background information on this topic, over the past decade, due to shrinking feature sizes and limits to silicon manufacturing, on-chip variation, or OCV for short, has had a growing impact on design closure. Today, 7nm and 5nm designs can see OCV effects impact timing just as much as nominal timing. At 65nm or 40nm, a flat derate factor was generally sufficient to model OCV. Using this method is very pessimistic because it attempts to capture the worst effects of OCV. However, because OCV effects at 65 or 40nm are generally very mild, this still allows the design to pass timing. As OCV effects increase in 28nm, using AOCV or advanced OCV reduces the timing pessimism by determining the cell's derate based on the number of logic stages in the shortest path, which is slightly more accurate than using a flat derate. POCV, or parametric OCV, increases the accuracy of OCV modeling by introducing a statistical mean and variance to model the variation of a cell. However, each cell is still modeled by a simple mean and variation. At 16nm, 7nm, and smaller process nodes, due to the severity of OCV effects, it's simply not feasible to take OCV into account and still meet power performance and area targets with these older methods. So, LVF, or Liberty Variation Format, provides the granularity and per-timing arc and pseudo combination needed to achieve a high level of precision on the amount of OCV applied. As shown here, increasingly granular methods of modeling OCV have been introduced over the past years as a measure to counter the increasing effect of OCV on static timing analysis, with LVF being the most precise and the main method of modeling OCV for advanced process nodes today. LVF is an excellent way of modeling OCV due to providing the ability to apply a precise amount of pessimism to individual timing arcs. How is LVF data characterized though? Well, each LVF table entry technically requires thousands of Monte Carlo simulations, which will make characterization run thousands of times slower. However, characterization tools typically have methods of reducing that to 3 to 10 times of nominal runtime, which is still a big challenge, but feasible. These runtime reduction methods may also make LVF characterized data more prone to errors and may completely invalidate your ST results if the errors are not caught. Because of that, validation of LVF information is extremely important. As mentioned earlier, the impact of LVF on timing and power can be as large as nominal timing, so it can definitely make or break a design. However, it's also very difficult to verify LVF data. Since the data is statistical in nature, what is the correct reference value to validate against? This is the question many library design teams face. Without the proper tools, LVF data validation may take months and still not catch issues reliably. Here are a couple of examples of LVF data problems. These results are objectively incorrect since statistical timing and power properties of standard cells or other IP isn't supposed to fluctuate wildly like shown here. However, this level of noisiness in .lit data is really quite common even in production LVF.lits. In the previous section, we looked at the design challenges at advanced nodes and how the manufacturers may potentially introduce design breaking problems if not handled correctly. Now, let's move on to defining a digital implementation methodology that addresses these challenges. What do we need in a digital implementation methodology for it to support advanced process node designs? The first design challenge we discussed was pre to post-route correlation. In order to achieve design closure that can converge from placement to post-route, we need an engine that bases its placement and optimization decisions on detailed routing topology. In addition, we also need our post-route STA to match up with earlier parts of the design flow, such as synthesis and floor planning. Therefore, we also need to verify all STA inputs, including time consistency between nonlinear delay models, or NLDM, and current source models, or CCS. Next, we also need a place and route engine that not only supports multi-core and multi-mode optimization, but is also able to handle a large number of MCM scenarios during optimization, and especially during ECOs. In that context, we also need a method to quickly and accurately produce the libs to cover all the additional PBTs required by optimization and sign-off, and make sure these additional PBTs are in alignment with the original set of the libs. Last but not least, we need comprehensive support for LVF all the way from full verification of the input LVF.libs to LVF support and path-based timing during optimization. Siemens provides a digital methodology which includes Solido Characterization Suite and Aprisa that is able to deliver on each of those requirements and provide a complete solution from accuracy verified inputs to a sign-off ready design database. We'll go into each of these in more detail later, but here's a summary. First, to ensure pre to post-route correlation, our approach starts with verifying that correct and precise inputs are provided through the place and route environment. Solido Characterization Suite provides comprehensive .lib verification, including NLDM and CCS consistency, and a full machine learning enabled check on all input .libs. Next, the Aprisa digital implementation solution utilizes a detailed route-centric approach that ensures that post-route correlation is built in to earlier stages in the flow. Aprisa also supports multi-core and multi-mode optimization in ECO and can read in large MCM scenario sets to support the increasing PBTs and modes required in advanced process node designs. To support this, Solido Characterization Suite uses machine learning to produce accurate .libs at PVD corners specified by the user to supplement the original set of .libs. And finally, both Solido Characterization Suite and Aprisa fully support LVF, including moments, throughout the entire flow, from .lib production and verification all the way to post-route stages. Used together, Solido Characterization Suite and Aprisa eliminate unnecessary margins to provide better quality of results while reducing time spent in design closure iterations. In the next two sections, we'll go through Solido Characterization Suite and Aprisa in more detail to explain how they deliver on the requirements for advanced process node designs. I'll start first with Solido Characterization Suite. Solido Characterization Suite is a machine learning-enabled Liberty model production and verification solution. It includes Analytics and Generator as two of its main components. Analytics is a comprehensive library verification tool, while Generator produces .libs and new PBTs. Both tools work on all types of .libs, such as standard cells, IOs, memories, even custom cells if we have .lib representation for them. The tools support all types of .lib data, such as timing, power, noise, and LVF data, including moments, which is important for advanced process node designs. Generator and Analytics are both characterizer independent, so they work with any library characterization flow today. They help design and library teams achieve better quality libraries, shorter and more predictable production schedules, and improve power, performance, and area in the final design. Solido Analytics is designed to be a lightweight, yet complete solution for .lib verification. Our users don't have to be experts in library characterization, although library teams will definitely appreciate what the tool offers. It verifies .libs using a combination of rule-based checks, machine learning outlier detection, and a full set of .lib comparison capabilities, all supported by a Liberty Visualizer GUI that allows users to quickly and effectively explore .lib content and investigate any issues that are uncovered. Overall, Solido Analytics helps library and design teams fully verify .libs in hours instead of weeks, and also helps digital implementation teams catch .lib issues before going into production. The rule-based checks in Analytics are fast and parallelized, provide all static checks required to make sure Liberty models are structurally correct, and also includes an API to add in any new validation rules not covered by the built-in rule set. Here's an example of the library visualizer being used to show a violation found from rule-based checks. We're using the CCS versus NLDM consistency rule as an example, which is used to check whether timing properties derived from CCS tables and the timing properties from NLDM lookup tables match each other. This is a check that's especially useful to ensure post-route timing and power analysis match that of the earlier stages in the flow. If a violation like this is found, the library visualizer can show the user exactly where the violation is from, as well as allow the user to click into any of the points of interest and show related information from those points. This is one of the many useful features of Library Visualizer, and in fact all of the plots shown earlier in this presentation that help identify potential issues with the libs like noisy LVF data and systemic outliers in certain PVTs were all provided by Solido Analytics. The machine learning outlier detection engine in Solido Analytics is one of its unique advantages. It starts with building a machine learning model of the entire .lib dataset. Then, by comparing all data points in the .lib to expected values in the machine learning model, analytics can identify outliers in the .libs. These issues include general spikes and noisiness in .lib data that are typically not detectable with other methods. The Library Visualizer interface provides the flexibility to customize plots and compare multiple Liberty files in minutes. Because it's connected directly to .lib data, it also allows for single-click .lib file entry from the GUI to explore the contents of the .lib files and quickly debug issues where found. .lib files at advanced nodes are notoriously large to the extent that text editors have a hard time handling them. Individual .lib file sizes can be more than 10 GB per file. Analytics has the capacity and performance to read in these large .lib files without slowdown, and is scalable to thousands of CPUs if needed. Because of this, many of our customers also use analytics as a .lib file explorer. Let's talk about Solido Generator. Unlike analytics, which is a standalone .lib verification tool, Solido Generator is a tool that uses machine learning to produce .libs and new PVD corners using existing .libs as anchor data. Place and route teams often need a particular combination of process corner and temperature that isn't provided in the original set of .libs. In many cases, setting up and running a complete characterization environment for the corners required isn't feasible. This is where Generator comes in. Shown here is a high-level flow of how Generator works. The user provides anchor corner .libs to the tool and specifies the required new PVT corners. Solido Generator then builds a machine learning model from these anchor .libs provided by the user in order to create .libs of the new PVTs requested. Generator is not a replacement for your characterizer tool. Rather, it's characterizing tool independent and can be used on top of your current characterizer to speed up .lib production because it uses machine learning to produce .libs as a fraction of runtime compared to SPICE. The minimum number of PVD corners depends on the library and process node, and we've worked with many customers to help them set up a flow that works for the needs. Once the required set of anchor .libs are characterized by SPICE, any additional PVTs can then be produced by Generator almost instantly. Some customers have asked us why they should use Generator instead of the voltage scaling capabilities in STA tools. Well, one reason is that Generator is much more accurate. We've worked with many customers that previously used voltage scaling or interpolation to substitute for missing corner .libs, and Generator's results have consistently been more accurate than STA voltage scaling. More importantly, Generator produces actual .lib files, so users can run the same kinds of checks and validations that they use for the original characterized libraries and validate the accuracy of Generator's results. These .lib files can also be used in other parts of the flow, such as multimodal multi-corner optimization. Compared to SPICE, Generator produces .libs about 100 times faster than SPICE characterization, meaning it can produce entire new PVT .libs in minutes instead of days. So place and route teams can quickly create accurate .libs that they need and not resort to using rough estimations while waiting for actual .libs to be provided. Since the tool uses .libs as inputs, there is no dependency on Foundry PDKs or SPICE methods. In addition, because Generator uses the existing .lib set as anchor data, the output is by construction already aligned with your original PVTs. This is important because many .lib providers have custom margins and offsets built into the characterized .libs, which causes any new PVT characterized from scratch to be misaligned with the original set of PVTs. To point out a couple of example use cases of Solido Characterizing Suite, here's a press release on Samsung's Foundry Design Technology team. Samsung uses Solido Characterization Suite to produce and verify the lips for their latest process nodes as part of the Siemens EDA machine learning toolkit that improves accuracy and performance of their IC verification flow. Another example is Hewlett-Packard Enterprise, or HPE, where their digital team uses Solido Generator and Analytics. Their main requirements were accurate and verifiable new PPT lips that would supplement the library set from the provider, and they needed a tool that provided these PPTs quickly, accurately, and without the flow complexity introduced by full SPICE characterization. Working on both standard cell and memory lips, the team was able to save hundreds of hours of runtime with Solido Generator. Using a modest 16 CPUs, they were able to produce a full set of required PPTs for a library consisting of about 1,200 standard cells, including LBF data, with an overnight run. This is in comparison to almost 2 weeks of expected runtime if the same number of CPUs were to be used for SPICE characterization. Memory.lib production with Generator took about 10 minutes compared to large runtime for the other methods that would have rendered the flow unusable. Before we start the place and route section of our presentation, I'd like to provide an update on our recent acquisition of Fractal Technologies. Fractal provides IP validation and comparison checks used by top-tier foundries, IDMs, IP providers, and fabless semiconductor companies globally. Fractal now joins the Solido product family, enabling Solido's machine learning technology to design IP validation across multiple views and formats, which allows us to provide a more complete solution for IP validation to further improve time to market and quality of silicon for chip design teams. Fractal's flagship product, Crossfire, is now known as Solido Crosscheck and provides a comprehensive set of about 350 and growing in-view and cross-view IP QA checks covering front-end views like Verilog, VHDL, the lib, and others, back-end views such as left, def, TDS2, as well as other views like SPICE and binary databases. It also provides an interface to cover any custom views required in your design flow. We're pretty excited about how our combined solution can provide a better solution to validating IP, ultimately resulting in faster design closure and better quality results. With that, I'd like to turn it over to Henry Chang, Senior Director of Product Management for Aprisa.
Thank you, Wei, for the introduction. In this section, we will go through how Aprisa addresses advanced node design implementation challenges. We discussed how pre-route and post-route timing miscorrelation could substantially impact time to design closure at advanced nodes. But how does the place and route tool handle this issue? Unfortunately, conventional place and route tools are mostly not designed to address this problem efficiently or effectively. Although other vendors claim their place and route system have integrated architecture, but under the hood, they are still old-fashioned, individual and sequential architecture. The engines in their system may be sharing the same database, but internally, each engine still builds its own data model. So, the placer data model is completely separated from detailed routes data model. So if the placer needs to access detailed routes attributes, it will have to go through some kind of ad hoc communication, which is usually not sufficient and not efficient. As a result, the designer has to use some technique to get around the problem. One technique is just to go through several iterations of pre-route and post-route stages. After each iteration, use the routing extraction at post-route to scale the resistance and capacitance at the pre-route stage. And hopefully, after several iterations, the timing can converge. This approach obviously will increase the time to design closure. Another approach is just to use some extra margin in pre-route stage to model the RC difference with post-route. This approach tends to put too much pessimism into your design and eventually hurt the final PDA. On the other hand, Aprisa is a place and route solution that is architected specifically to address this problem. Aprisa is a full-fledged netless to GDS physical implementation tool. At the center of its detail route-centric technology is the unified architecture and the unified runtime data model, which means that through the entire place and route flow, each engine can access to all the objects and attributes of all other engines. That includes placement, routing, timing, RC, DRC, EM, IR, etc. So, the placer have complete and consistent detailed route visibility to accurately predict the timing of the design, and the timing will be well correlated with the final post-route timing. Therefore, the design can be converged with less iteration and achieve better PPA. Aprisa can also correlate very well with sign-off STA and DRC tool. Aprisa supports LVF and path-based analysis natively during timing analysis and optimization. This helps to reduce the unnecessary design pessimism and improve the design PPA. Aprisa also has a unique adaptive MCMM methodology that can enable many MCMM scenarios to be covered during the place and route with manageable runtime and memory. This will improve the correlation with the sign-off timing and dramatically reduce the effort for timing ECO. Aprisa is also certified by leading foundries down to 40 nanometer, and it has a proven track record with thousands of successful customer tape-out. So, how does Aprisa solve the pre-route and post-route miscorrelation issue at advanced node? On the left-hand side, it is the terrible 7 nanometer correlation issue from conventional placement-centric place and route tool that we just showed earlier. On the right-hand side, you can see that with Aprisa's detailed route-centric technology, the correlation between pre-route and post-route timing becomes much better. This will dramatically reduce the number of pre-route and post-route iterations and improve the final PPA of this design. In addition to the pre-route and post-route correlation issue, designs at the advanced node also face the challenge of lengthy ECO process, which usually is caused by miscorrelation between place and route and sign-off STA. Aprisa has many unique technology that can improve the correlation with sign-off STA timing, and hence reduce the ECO effort and the overall time to design closure. The first technology is adaptive MCMM. As you know, advanced nodes now require over 100 of MCMM scenarios to be signed off by STA before tape-out. However, conventional place and route tool cannot support such a large number of scenarios. As a result, a practical approach is to only pick a small number of dominant scenarios for place and route, and use post-route timing ECO to clean up the remaining scenarios. However, this approach inevitably will cause many ECO iterations and prolong the time to design closure. So, Aprisa's adaptive MCMM is a technology that can allow design to put most of the sign-off MCMM scenario into place and route. So since most of the scenario has been covered by place and route, the ECO effort becomes very minimal. Adaptive MCMM can accomplish this without dramatically increase the use of eCPU and core memory. This is because adaptive MCMM has three techniques. The first technique is called smart selection, that will automatically identify a subset of effective scenarios for your precinct. The selection is done in a way to minimize the impact to the sign-off correlation. The second technique is intelligent grouping, which will maximize the use of the available CPU and memory of your server and perform efficient timing analysis and optimization. The final technique is concurrent optimization, to simultaneously optimize timing at all effective MCMM scenarios to achieve fast timing closure. Overall, with adaptive MCMM, a preset can cover large number of MCMM scenarios during place-and-route optimization, so the number of ECO iterations can be reduced, and at the same time, achieve better PPA. LVF is the most advanced OCV methodology, and it is required by Foundry for advanced processing. The LVF support is not only needed for sign-up STA, but it is also needed during place-and-route timing optimization. With native and precise support of LVF, place-and-route can avoid unnecessary timing pessimism and reduce over-design, so eventually improve design PPA. The precise support of LVF is well correlated with sign-up timing, so it eliminates unnecessary ECO iterations and improves time to design closure. There are two main methodologies for static timing analysis: graph-based analysis and path-based analysis. Graph-based analysis assumes the worst-case timing when calculating the delay of each gate. Therefore, the resulting timing tends to be more pessimistic. On the other hand, path-based analysis takes into account the actual condition of each gate in the timing path to determine the path delay. Therefore, the path-based analysis timing is more realistic and less pessimistic. But the computation and memory costs for supporting the methodology can be very expensive. As a result, while sign-off STA support both GBA and PBA, conventional place-and-route tools mainly support graph-based analysis during timing optimization. This pessimistic timing during optimization tends to cause over-fixing and over-design, hence degrade the final quality of the result. In a preset, we have a patented technology that can support PBA analysis natively during place-and-route optimization. This can help to reduce the over-design and improve the quality of the result. As you can see in the table, after using PBA during a preset optimization, the timing is less pessimistic, and hence substantial power can be recovered. Some of the data even show that the power is reduced by over 30%. With this slide, I'd like to use a customer case to demonstrate the preset's fast time to design closure and PPA. In this case, our customer used both a preset and another competitor's place-and-route tool for this 14nm quad-core CA57 project. One interesting thing is that this customer allocated two teams to do the project using two different place-and-route tools. At the end of the day, they want to see which tool can complete the design first and what is the PPA. As you can see, a preset performed very well in this project. It not only completed the project much earlier than the competition, it also achieved 10% better timing and 10% better power and area simultaneously. This is very unusual because, as you know, higher frequency usually causes higher power. But a preset delivers not only higher frequency, but also lower power. As a result, the design team VP said in a quote that a preset enables us to significantly reduce area and power while increasing the performance of our latest design. In fact, this kind of feedback happens quite often within our customers. Here we summarize a few feedbacks from our recent customer project. As you can see, our customers are using Aprisa very successfully on a wide range of applications, such as networking design, image sensor, power management, graphic core, process core, mobile design, and military and aerospace IP. Aprisa also performed well for not only at the advanced node, like 7 nanometer, but it is also very good for 16 nanometer, 65 nanometer, even 180 nanometers. So, if we summarize the common feedbacks from our customers, you can see that Aprisa is very well correlated with sign-off tool. Very good pre-route and post-route correlation. Very easy to adopt. One reference flow can apply to all their design. And very competitive PPA. So overall, Aprisa has fast design closure with better PPA. Finally, I would like to summarize today's webinar. We talk about the increasing process and the design complexity at advanced node is making the design closure much more difficult. This includes worsened process variation, exploding number of MCMM scenarios, impact from the resistance domination of design timing, and the growing number of complex IP. Through our webinar, I hope you learned that the combination of Solido categorization suite and Aprisa place and route solution can help to reduce the time to design closure of your design project. You can leverage the machine learning-based Solido generator to reduce your .lib generation time by more than 100x. You can also validate your .lib with Solido Analytics to detect any defect early before they cause any expensive delay for your design. Finally, you can adopt Aprisa detailed route-centric place and route technology and the excellent correlation with sign-off to reduce your time to design closure and achieve better PPA of your design. So, thank you very much for attending today's webinar, and we invite you to contact Siemens EDA for more information and education. Thank you.
Welcome to our presentation on accelerating time to design closure and silicon success for advanced process node SoCs. My name is Wei-Li Tan. I'm a product manager for the Solido Characterization Suite at Siemens EDA, and I'm joined today by Henry Chang, Senior Director of Product Management for the Aprisa Group at Siemens EDA. We'll start with a recap of the main challenges on design closure at advanced process nodes and cover the digital methodology requirements for this category of designs and how they're addressed. After that, we'll describe how Aprisa Digital Implementation and Solido Characterization Suite address these challenges, along with results and example case studies of applying these methods in production flows, followed by a summary and wrap-up. Let's start with advanced node design challenges. Digital implementation has evolved throughout the past couple of decades, from 65 nanometer process technology to the latest cutting-edge 5 nanometer and smaller nodes. Due to silicon manufacturing limits, smaller transistor and interconnect feature sizes, and designs becoming more complex in general, several challenges have emerged for digital implementation teams. One of these challenges is pre-route to post-route correlation. As process technology shrinks, wire widths become extremely thin, especially for multi-patterning metal layers. Because of this, resistivity has become the main contributor to timing in traditional flows. This introduces a larger number of iterations needed for design closure and extra margins padded at the pre-route stage, which generally causes over-design and ultimately suboptimal power, performance, and area in the final design. Another design challenge is that the number of process, voltage, and temperature corners, or PVT corners for short, have increased drastically. Coupled with additional sign-off timing modes, this results in more than 100 multi-corner multi-mode or MCMM scenarios that have to be evaluated during sign-off. In addition, the effects of on-chip variation, or OCV, have become a major factor in. Hi, and welcome to our presentation.